Hey guys, it's Dr. Franklin and I'm back again with another tutorial video. This one will focus on the one sample t-test. The one sample t-test is employed when you're trying to assess a significant difference between a sample mean and a population mean, and you do not have the population standard deviation. Let me go ahead and lay out for you the formulas that you'll need to utilize within this particular type of problem. One is the variance, and the variance is represented by a lowercase s with a superscript of 2, and in the denominator we have n minus 1. Another formula that may come in handy is this one. This is the standard error of the mean. In particular, it's the estimated standard error of the mean. And in the numerator, we have the sample variance, and the denominator, we have a sample size. And then you're going to take the square root of all of that. So this type of problem this type of statistic is employed when you don't know the population standard deviation, and the estimated standard error of the mean is a way to estimate the population standard deviation utilizing sample statistics. Finally, there is a one sample t-test formula. T equals capital M minus mu over the estimated standard error of the mean. So just as a recap, I'm going to identify what these abbreviations are. This is sum of squares, also known as sum of squared deviation scores. So recall that en route to calculating a sample standard deviation, you have to calculate deviations, which is just the distance that a raw score is from the mean, square each of those deviation scores, and then sum your deviation scores. And we're summing our squared deviation scores so that we can move forward and get our variance. In this particular case, sum of squares is just a precursor to the variance, and that's why you see it in the numerator there. In the denominator, we have degrees of freedom. And this is a pretty simple formula. It's just a sample size minus 1, that 1 representing that numeric that has to be a certain amount in order for all of the deviation scores above a mean and below the mean to balance out around the mean once you sum up the deviation scores. I know that's a mouthful, but just rewind this back. S square, variance, n sample size, SM, estimated standard error of the mean. And then in this numerator for your t-statistic, you have a population mean, and you have a sample mean. Be careful when you see the abbreviation for the estimated standard error of the mean to not assume that this is a equation. In other words, you won't actually do this out. You won't multiply sample standard deviation by the mean, okay? But really, I want you to recognize that this is a symbol within itself. So once again, this is a formula that you use when you don't have the population standard deviation. So let's work an example. Let's suppose a psychologist has prepared an optimism test that is administered yearly to graduating college seniors. The test measures how each graduating class feels about its future. And the higher the score, the more optimistic the class. Last year's class had a mean score of 15. So let me jot that down. And a sample of non-seniors from this year's class was selected and tested, and that sample yielded a mean of 10. Let's say that sample consisted of non-seniors, and the sum of squares is 94. Now let's say in this problem that we were given an alpha level of 0.05, and it is a two-tailed test, and we are given the task of determining if there is a significant mean difference between the non-seniors of this year and the score of 15 that represents the population of last year. So because it is a two-tailed test, we know that we will have a unidirectional alternative hypothesis, and that basically means that we will simply be looking to see if there's a significant difference that is occurring beyond chance, and we're open to that difference being on the high end or on the low end. Based on the sample characteristics that we have, it appears that this sample mean of 10 will be on the low end or to the left of the population mean, given that it is lower than the population mean of 15. So if we were to work through our steps in terms of hypothesis testing, step one would involve specifying our zero effect hypothesis or our null hypothesis, as well as our alternative or our research hypothesis. We would specify it like this: population mean equals 15. In other words, just because we are looking at a different year does not mean that we're going to see a significant difference in terms of optimism scores. The alternative hypothesis would say that no, we will see a significant difference. In other words, because we're looking at the optimism scores that are occurring this year, there's an anticipation that it's going to ultimately change the population mean from 15 to cause it to be something else. So that's step one, just laying out our hypotheses. Step two deals with locating the critical region. And in order to locate the critical region, you need three key pieces of information. You need your degrees of freedom, and in this case the formula for that is n minus 1. So we have a sample of non-seniors, so our degree of freedom can be gained by subtracting 1 from 9, and that will yield us 8. We will need our alpha level, which is 0.05, and we will also need whether or not it's a two-tailed test or a one-tailed test. We know that it's a two-tailed test, as we previously discussed. So we're going to take all of this information and go to our t-distribution table so that we can ultimately obtain our t-critical, which will serve as a significant factor in our decision to either accept the null hypothesis or reject the null hypothesis. So let's switch gears and pull up this t-table. So you utilize the t-table by first going to the row at the top of your t-table that corresponds with the type of test you are performing. So we are performing a two-tailed test, so that means we will go with this first row immediately above the degree of freedom row. And since we are indeed going with an alpha level of 0.05, this is going to be the specific column that we elect to utilize. So we just took two pieces of information, the two-tailed test information as well as the alpha level, and used that to identify the column. Now we need to employ information related to the degrees of freedom in order to find our t-critical. Our degree of freedom is 8, and once we locate that within the t-distribution table, we will basically go to the t-critical region boundary marker that intersects with the two-tailed test and alpha level column. So that would cause us to come over, come over, come over. As Kenny Chesney said in one of his songs, come over, come over, come over, come over, come over. Okay, you guys know nothing about country music. Okay, fine. Anyway, our T critical for this example will be 2.306. Because it's a two-tailed test, it is going to be positive and negative 2.306. Okay, so going back here, plus negative 2.306. Okay, so we did step one, we did step two. Now the next thing that we have to do is work through our steps in order to calculate our variance, our estimated standard error of the mean, and our t. All right, guys, so let's continue to move forward with calculating our t statistic in terms of the hypothesis test procedure. We are now on the third step, calculating the statistic. Let's start off with our variance. So we have our sum of squares, which is 94, and we're going to put that over our degrees of freedom, which is 8. And when we divide 94 by 8, we end up with 11.75. From there, we move on to calculate our estimated standard error of the mean, which involves the variance in the numerator over the sample size, and then we're going to take the square root of everything. Be very careful not to stick a standard deviation within this numerator and try to square it. Okay, I want you to look at this entire abbreviation and superscript as representing what you're calculating here, which is the variance. In essence, a variance is the squared standard deviation. So it makes sense from that standpoint, but don't get too hung up on that, thinking that you need to calculate the sample standard deviation, then plug it into it and square it. Just don't. Just drag whatever you got at step one down into this numerator here. Okay, so in our case, we're going to stick 11.75 in the numerator over your sample size, which is 9, and you'll take the square root of it. 11.75 divided by 9, and then the square root is taken, you should end up with 1.14. And then finally, you will calculate your t. Your sample mean is 10 minus 15 over 1.14. And when you do the numerator out, you end up with negative 5 over 1.14. And then negative 5 divided by 1.14 yields you negative 4.39. So all of this, guys, is step 3 in terms of hypothesis testing. And then finally, step 4 involves you actually making a decision. Is there a significant difference between the optimism scores of this year's seniors and the optimism scores of the previous population's graduating seniors? Step 4 involves making a decision. Now, you've determined that your T critical region boundary markers on both ends of the graph is 2.306. And the shaded areas represents regions of rejection for your null hypothesis. This is the region of acceptance for the null. We obtained a negative 4.39. That means that our T statistic falls into the region of rejection, and we will be rejecting our null hypothesis, and we will accept this research hypothesis. All right, so we finished the problem, but I want to talk about some problems or some scenarios that you may be given in your end of the chapter problems in which you may not be given the sum of squares. Sometimes you may be given a sample standard deviation. And this has the potential to throw people off because the formulas that we've talked about have involved the sum of squares and degree of freedom. So some people, if they didn't have the sum of squares, may look at that sample standard deviation and go, well, how am I supposed to make my way through the calculation of this formula? Well, if you're given a sample standard deviation, what you will need to do is simply square that sample standard deviation to get your variance. In other words, you would take the sample standard deviation and square it, and once you square it, you will end up with 11.75. Okay, if you take the square root of 11.75, you will go back to 3.42. So the reason why you can just square the sample standard deviation to go back to the variance is because ultimately, in order to get the sample standard deviation, you have to take the square root of the variance. Squaring something and taking the square root of something are polar opposites in terms of mathematical operations. Recall that the formula for a sample standard deviation is sigma x minus m squared over degrees of freedom, and then eventually you have to take the square root of everything, right? If we take away the square root piece right here, then you will notice that what's left is the variance formula, sum of squares over n minus 1. Okay, so again, if you're just given a sample standard deviation formula, square it, you'll go back to the variance, and then you don't even have to worry about this step, okay, because s squared equals sum of squares over n minus 1 is the equation for the variance. Once you get the variance, then you can just simply plug it where it needs to go and move throughout that equation and then complete your last equation that's dealing with the t. If you're just flat out given the variance, which wasn't the case in this example, of course, then you don't even have to worry about step 1. Okay, you just immediately jump to step 2 and you move that variance where it needs to go. Okay, and then finally, if you're given the sum of squares, then you just move through the operations that we've completed over the course of this video. The last thing I want to talk about is the writing of your null hypothesis as well as your alternative hypothesis. This was a two-tailed test, so our alternative hypothesis just indicated that there would be a difference. But sometimes you may be given a one-tailed test, and one-tailed tests indicate a specific direction: significantly higher, significantly lower, significant increase, significant decrease, etc. Okay, you'll usually be cued somewhere in the problem as to what type of alternative hypothesis you should assume. When you're constructing your alternative hypothesis, if you're dealing with a significant increase, as it relates to this example, a significant increase of optimism scores, then you'll want to make sure that you're indicating greater than within your alternative hypothesis. If it's speculated that it's going to lead to a significant decrease, then you'll want to make sure that you're indicating lesser than. All right? So in order to figure out which way to go and how you should write out your hypothesis, pay attention to the research literature that's being covered in a problem that you're completing. And once you get to the last bit of your problem that's specifically telling you what type of difference you'll assess, whether it's just a significant difference or significantly more, significantly less, significantly higher, significantly lower, significant increase, significant decrease. Pay attention to those wordings because that will give you an indication as to how to construct your alternative hypothesis. So, with that said, I hope that this is helpful, and make sure that when you find your t critical in your t distribution table, make sure that you're going to the one-tailed row and you're going with signage, because it won't be positive and negative. Make sure you're going with signage that corresponds with your alternative directional hypothesis. Let me know what you think in the comments below, and feel free to let me know what you think in person as well. Take care.